Welcome to video 2 of the physiology review for the myasthenia gravis case. This is the next mastery question associated with synaptic transmission. What is most likely to be the neurotransmitter released in an excitatory synapse? So this is my way of saying I expect you guys to know the neurotransmitters and what sorts of synapses you'll find them in, and generally speaking what they do. The only neurotransmitter that we covered for excitatory synapses, if you don't count the neuromuscular junction, is glutamate. That is the one that I will expect you to know. My bet is that Dr. Hepner will expect you to know more, probably in the brain, behavior, and cognition block. But for my purposes, for physiology, this is the only one that we covered as a typical example. Now, there are actually two types of glutamate receptors. These, again, are in excitatory synapses. Again, with skeletal muscle, you're going to get one big end plate potential that's going to be really big, and you're going to have threshold potential every single time if the muscle is working correctly. That is not true in the central nervous system, where you may have a lot of excitatory synapses onto one neural cell body, and those synapses will have to add up, and eventually you'll get to the threshold potential, or you won't. It'll fall back down to rest. But it typically doesn't happen with just one stimulus. When you think about it, if you think with your brain, you have a lot of different things coming in. And there are a lot, this is the way that I think of it in my own simplistic way, there are a lot of factors that come into making a decision. So you have a lot of synapses firing, and eventually, poof, you make the decision, right? But it depends on a lot of different inputs and the same thing's happening here. Whether you want this cell to fire or not probably depends upon a lot of different inputs. And whether it fires or not depends upon the sum of those inputs, inhibitory and excitatory. So there are usually many EPSPs that add up to, or some, to either allow you to hit the threshold potential or not. Typical EPSP, very small, 1 to 2 millivolts. And again, these summate, and we did cover that as part of the synaptic transmission lecture. So glutamate receptors are the channels that we covered, and these are non-specific cation channels, as are the nicotinic ACH receptors that we covered for the neuromuscular junction. Both sodium and potassium go through the channel. Sodium comes in, potassium goes out. The net effect is to depolarize the membrane, okay? So don't let that confuse you. We have two types of receptors, non-NMDA and methyl D-aspartate and NMDA. N-methyl D-aspartate is not a physiological ligand. Glutamate is the ligand in the body that binds to these receptors. The reason why we specify non-NMDA or NMDA is because in the laboratory, this is the way that you distinguish between the two types of receptors. One type binds NMDA, the other one doesn't. And so they're typically called non-NMDA or NMDA. Don't let that confuse you, though. Physiologically, they both bind glutamate, and that's how they act, okay? This is not a physiological ligand. The non-NMDA, strictly ligand gated, the glutamate binds, the channel opens, you get depolarization. The NMDA, the same thing happens, but you also need a postsynaptic membrane depolarization in addition to the glutamate binding. In other words, glutamate binding on its own isn't enough to cause the NMDA receptor channels to open. You actually have to have depolarization due to something else as well. And these are permeate to calcium as well, which, as you know, is a second messenger. And so these receptor channels can open and cause a variety of things to happen in the neural cell besides just more depolarization, okay? Okay. That was it for the synaptic transmission mastery questions. I'm going to go through the review mastery questions now. for the establishment of the resting membrane potential and the action potential. Just as a refresher for those of you who wish to hear it again. So I don't know why that happened, but let's get through. There we go. We're back. Maybe I bumped the board or something. Each of the two cells represented in the graph below is the same size, which has the thicker membrane. Thicker membranes means reduced capacitance, and our capacitance is the slope of the relationship between voltage and charge. So if I have a low capacitance, that means it takes less charge to attain a given voltage, which means that the membrane it's easier to change the membrane voltage, it's easier to depolarize that membrane, it's easier to fire an action potential in that membrane, which is why we cover this. The cell with the reduced slope is cell 2. It therefore has the reduced membrane capacitance, and therefore it is the one that likely has the thicker membrane. And I would remind you that cell membranes generally don't vary in thickness, but you do get myelinated neurons, which effectively thicken the membrane. So myelinated neurons transmit action potentials much faster because effectively, in large part, because the capacitance is reduced by the fact that the myelin is wrapped around the membrane and it's reduced the capacitance. And that's why we cover this, okay? So that's the take-home message. A resting membrane has the following permeabilities. The resting potential will be closest to the equilibrium potential of which ion? Well, we just talked about the fact that the chloride ion, the equilibrium potential is equal to the resting potential. And so that one is the one where it will be closest. If chloride were not here, then it'll be the ion with the highest permeability, and that would be potassium. So potassium has an equilibrium potential of minus 95, sodium of plus 60. The membrane potential typically much closer to minus 95, and a muscle cell probably something like minus 80 or something. And that is because the permeability of potassium at rest is much higher than to sodium. So you may ask yourself how this comes about. We have a voltage, a membrane voltage that is not changing. So what that means is that the amount of charge, let's say positive charge coming in, is equal to the amount of positive charge going out. So that means that we have an equal amount of sodium current and potassium current. And you may ask yourself how that could be when the permeability of potassium is so much higher. So the reason lies in this equation, Ohm's law. 90% of life showing up, the rest is Ohm's law. So Ix, X is the ion, is equal to the permeability of that ion. This is the conductance, same thing. Times the difference between the membrane voltage and the equilibrium potential. This means that the sodium current is equal and opposite of the potassium current if you have a resting membrane voltage, that is a voltage that's not changing, okay? So how can this be? Here's our equation for sodium. We have a low sodium permeability, but E and A is very far away from the membrane voltage. So this term is high, this term is low. You look at the potassium side, the permeability is high, but because the equilibrium potential is very close to the membrane voltage, this difference is low. So that's how these two can be equal and opposite. This can be a lot different from this, as long as this voltage difference between these two equilibrium potentials balances that out, okay? So in the case of potassium, we have a high permeability, a low driving force for potassium to exit the cell. In the case of sodium, we have, in the case of potassium, a high permeability, a low driving force. In the case of sodium, a low permeability, but a high driving force for sodium to enter, okay? And so these are equal and opposite, you get a resting potential, okay? So that's why that is. A cell has the following potassium concentration inside and outside. What is the equilibrium potential? It's plug and chug into the Nernst potential. Log of 6 over 140 times 61 gives you an EK of minus 93, okay? That is relatively easy. Remember, I did ask you to memorize the Nernst potential. Nernst equation, you should do that. what is the state, open and closed or closed, of the fast sodium channel and delayed rectifier channels at a typical resting potential of minus 90? So in the case of potassium, here is our probability that our activation gate is open. Here is our voltage. As the voltage rises towards zero and then goes beyond zero, the activation gate is more and more likely to be in the open state. So at a resting potential of minus 80 or so, pretty much all those channels are closed. So your delayed rectifier sodium channels are pretty much closed at rest, okay? And that is here, okay? For sodium, it's the same situation. The activation gate is more likely to be open at any given time. It flips open and closed, but it's going to spend more and more time open the higher this voltage goes up, or you're going to find it in the open state more and more. At minus 80, this activation gate mostly closed, and at minus 80, the inactivation gate mostly open. And this is the state that we want our sodium channel to be in. We want our activation gate closed, our interactivation gate open, so that when that membrane voltage goes up, the activation gates will flip open and sodium will flow into the cell, okay? So you have a patient who needs a minor wound treated. You administer a local anesthetic. What is the likely mechanism of action? It is likely going to be blockage of sodium channels. Remember, fewer sodium channels means a higher or less negative threshold potential, okay? And therefore, you will be much less likely to fire an action potential in that situation. Increased potassium causes the membrane to be less excitable. Why is that? Okay, this is a multi-step process. If you increase extracellular potassium, you cause its Nernst potential to go up. So its Nernst potential, let's say it's normally minus 95. If you increase the extracellular potassium, let's say it goes to minus 60 or something, okay? So what that means is that, you've got your open potassium channels at rest. They're pulling you down to a minus 95 normally. Now you add extracellular potassium, and instead of pulling you down to a minus 95, they're pulling you down toward minus 60. So your resting potential rises as a result of that. And when your resting potential rises, you get what's called resting inactivation of sodium channels, where the sodium channels, instead of being the inactivation gates being mostly open at minus 60, they're mostly closed. So you have fewer sodium channels that are available to open. When I try to fire an action potential and I make the membrane voltage go up, if the inactivation gate's already open, then all I have to do is open the activation gate. But if it's closed, I can open the activation gate all I want. No sodium is going to go through as long as that inactivation gate is closed. So you get what's called resting inactivation of sodium channels, and that causes your resting potential to go up. And as a result, your membrane becomes less excitable due to the resting inactivation of the sodium channels. So here's our Goldman-Hodgkin-Katz equation. And again, increased extracellular potassium makes this membrane voltage go up, just like that. Okay. Action potential spread through the heart from fiber to fiber, starting at the SA node. It's slower in the AV node. What factors could be responsible for this delay? I know we're not talking cardiac anymore in this block. This is my way of asking you what factors could slow action potential propagation. So the answer to that is first, cell fiber diameter could be smaller. If the cell fiber diameter is smaller in the AV node, then that would cause your action potential to slow down. Bigger cells propagate action potentials faster. That's not the case in the SA node, but it's a possibility in any cell with slow action potential propagation. The resting membrane resistance, this is the electrophysiological way of saying the number of open potassium or chloride channels. The more open channels you have at rest, the lower the resting membrane resistance. Low resting membrane resistance means slow action potential propagation. Okay, so that would also be a potential reason why you might have slower propagation through the AV node. As it turns out, that is not the reason in the AV node. The intracellular longitudinal resistance could go up, and that would slow the action potential propagation. This usually does not vary, except when you're talking about cells that are hooked together through gap junctions or electrical synapses, as you find in the heart. And in that case, if you have fewer gap junctions, then your longitudinal resistance, that is the ease with which current flows from cell to cell, the resistance will go up if you have fewer gap junctions. High resistance would slow action potential propagation. That turns out to be a major reason why the AV nodal action potential propagation is slower and the AV nodal delay is what it is. You actually do have fewer gap junctions in between cells. And finally, the number of sodium channels. If you have a reduced number of sodium channels, your action potential propagation will be slower. It turns out that is the case in the SA node. There are virtually no voltage-gated sodium channels. Instead, you have calcium channels that carry the upstroke of the action potential in the AV node and in the SA node. That calcium carries significantly less current. So the substitution of calcium channels for sodium channels, what you've done is you've reduced the number of sodium channels, and that will slow that action potential propagation. Even though the calcium channels are there, they're much less effective than sodium channels at carrying that current and generating action potentials. Okay, so it's equivalent. Well, it is a reduced number of sodium channels, in addition, the fact that there are calcium channels there instead of sodium channels keeps that propagation slow. And finally, we talked about the membrane capacitance. If the capacitance is low, you get fast action potential propagation. In theory, you could have a high capacitance, and that would slow it down. That is generally not really a major reason why you get slower action potential propagation in the AV node. Our next mastery question, Purkinje cells spread the action potential rapidly along the endocardium, causing a nice even contraction. What is a factor that could be responsible for the rapid action potential propagation of Purkinje fibers? This is my way of asking the same thing that I just asked the slide before. In this case, you're looking for factors that would increase propagation speed, and I just went through all of these. It would just be a change in the opposite direction. Okay? Why does the delayed rectifier potassium channel need an inactivation gate? Not need an inactivation gate to close like the sodium channel does. The reason is because in the case of potassium channels, the more potassium channels you open, the more you drag the voltage back down. So in a way, the potassium channel closes itself. The more I open, the more potassium flows out of the cell, the more the membrane voltage drops. And so eventually what happens is the membrane voltage drops such that the potassium channel closes on its own. You don't need an inactivation gate to close it, because as the voltage goes down, it'll close just due to the fact that the activation gate closes. Remember, we call that deactivation. In the case of sodium channels, that is not true. More sodium channels opening means sodium influx. It means more depolarization. The only way that channel is going to close is if you have that inactivation gate close, and then that will shut off the sodium influx and the voltage will drop, probably due to the potassium channel flux. And as that happens, then the activation gates close again. But if I took this inactivation gate away, the sodium influx would just continue, and you continue to have depolarization, and this activation gate would never close. I asked the question, what are the characteristics of all action potentials? This is the stem of the question, if it appears on a readiness assessment. All APs are all or none, that is, they either fire or they don't. They're non-decremental, means the peak voltage remains the same all the way across the cell. They are unidirectional, meaning they only propagate in one direction, because as your action potential propagates, the membrane behind that is refractory for a certain period of time, and so the action potential can't propagate back on itself. Again, they have refractory periods, just like I said, a period where the sodium channels or calcium channels need to recover from inactivation, or the inactivation gate will open again when the voltage comes back down. All action potentials have potassium currents. That is true. Potassium currents are needed to bring the voltage back down again. However, note that some tissues do not have fast sodium channels, and they are basically absent, and that would be like the SA node and the AV node, where calcium carries the phase zero or the upstroke of the action potential. What would increase the threshold potential? Fewer sodium channels would make that threshold potential less negative or increase the threshold potential. And that is because you have to open a higher percentage of the channels that are left in order to get that regenerative reaction to take place. Increased resting membrane permeability. More open potassium or chloride channels means that your membrane voltage is being dragged down more. And so you need to open more sodium channels to oppose that and get that regenerative reaction going in order to get a phase zero of an action potential. And a decreased rate of depolarization from rest. Remember that we went through that. The slower the depolarization, the higher or the less negative the threshold potential. And that's because you give the inactivation gates on the sodium channels time to close as that voltage goes up, and so you shut off the sodium channel and the sodium current doesn't flow. Okay? All right, that's the end of my video review for the myasthenia gravis case. Good luck, guys.